Welcome to a chemical kinetics screencast on the effect of temperature and activation energy. Remember when we started this unit on kinetics that we saw there were several factors that affect the rate of a chemical reaction, including concentration, temperature, whether there's a catalyst or not, and how easily the molecules are able to interact with each other. Now, we've spent a fair amount of time so far looking at the effects of concentration on reaction rate, and now it's time to look specifically at the effect of temperature on rate of reaction. Now, remember that if the temperature is low, then molecules on average travel at fairly low speeds and have fairly low kinetic energies. And if two molecules that are low temperature molecules traveling at relatively low speeds collide with each other, then those molecules just simply bounce off of each other because the collision does not have enough energy for the molecules to react. So here we have a molecule made up of two red atoms, let's call it A2, molecule of two blue atoms, let's call it B2. They collide with each other and they simply bounce off and stay intact because they're not energetic enough for a reaction to occur. And this is something like if you have a minor fender bender with somebody in a parking lot, both cars are traveling at very low speeds, they just bump into each other's bumpers, they bounce off, no damage is done because there wasn't enough energy, enough kinetic energy of either of the traveling vehicles. Now, if instead we have high temperature, then the molecules on average are traveling faster. Average molecular speeds are higher and kinetic energies of molecules are higher. And if two molecules collide with high enough speeds, then what can happen is that the molecules can react with each other. And the reason is because the collision might have enough energy to break chemical bonds, and then new bonds can reform or can form, and then we've caused a reaction. So here molecule A2 and B2 collide with each other, but they hit with enough energy to break the bond between the two A atoms, break the bond between the two B atoms, and then A and B stick together and make new molecules. So this collision was energetic enough to cause bond breaking and cause a new reaction to take place. Kind of like if two cars collide with high enough speeds, then you're going to have some rearrangement of the structure of the cars. Now, the minimum energy needed for a reaction to occur is what's called the activation energy. And the activation energy graphically can be represented as shown here, where on the x-axis we're graphing the progress of reaction, so start with reactants on the left, form products on the right. On the y-axis it's energy, and if we start with reactants that have a certain amount of energy and end up with products that in this case have a lower energy, so this is an exothermic reaction because the products are at lower energy than the reactants, energy is overall given off, then notice that the reaction to take place, these reactants have to overcome this activation energy barrier or activation energy hill before they can form products. So the height of this barrier is what's called the activation energy, and the molecules have to have enough energy to make it to the top of this hill. If they do, then they'll roll downhill, so to speak, energetically and end up forming the products and the reaction will take place. But if the colliding molecules don't have enough energy to make it over the top of the hill, they'll roll back, so to speak, bounce off of each other, stay intact as reactants. Now, perhaps you remember this from Chem 1A, what's called the Maxwell-Boltzmann distribution of molecular speeds, or we could also do this in terms of kinetic energies. And this is a graph of kinetic energy of molecules versus number of molecules. And perhaps you remember it looks something like this. We have a small number of molecules with very little kinetic energy, a small number of molecules with a very high kinetic energy, and then this sort of distribution with most molecules having some in-between, middle-ish kind of kinetic energy. Now, the activation energy corresponds to the amount of energy needed to make a reaction occur, amount of energy the molecules have to have when they collide to break bonds and form new bonds, and perhaps the activation energy for a given reaction is shown here. And notice that only this small fraction of molecules here is going to have enough energy to overcome that activation energy barrier. Molecules with less energy than that don't have enough energy to surmount the activation energy barrier, and they won't lead to a reaction. Now, what happens if we go to a higher temperature? Hopefully you remember that this distribution of molecular energies is going to shift, and if we go to a higher temperature, if we increase the temperature, then this distribution shifts to the right. We have a lower peak, but more importantly for our purposes, we have more high energy molecules, more high speed molecules, and notice now there's a larger number of molecules that have enough energy to surmount the activation energy barrier. So at a higher temperature, the distribution shifts towards higher average speeds, higher energies, and therefore a larger fraction of molecules that can undergo reaction. Here's another graph of this, and then just a note that the number of collisions that have at least activation energy E sub A, those are going to be the molecules that are able to react, and that's going to determine the rate of reaction. And again, E sub A here stands for activation energy. And the molecules highlighted in blue, or the shaded in blue here, would be the molecules that have enough energy at a low temperature. The molecules in red plus the ones in blue, or the areas that are shaded, that are the ones that would have enough energy at a higher temperature, which is, of course, quite a few more. Here's an example of a reaction you've seen before, the iodine clock reaction. This is the one we did in lab. And note, at room temperature, we have a rate constant that is a certain value. And some groups did this reaction at a higher temperature, and they should have gotten a higher rate constant than the groups that did it at room temperature. And then here's some sample data for a lower temperature group, and this is a lower value of the rate constant. And what this goes to show is that the temperature dependence of a chemical reaction is shown in the rate constant for that reaction. So here's our summary of that. The rate constant is where the temperature dependence of the rate of the reaction lies. That's because of more molecules with more energy, which can overcome the activation energy barrier. And the mathematical relationship between the rate constant and the temperature is what's called the Arrhenius Equation. And here it is. The rate constant K is equal to what's called frequency factor, capital A, more about that in a little while, times e to the negative E sub A over RT, where the exponent of E is the activation energy, E sub A, divided by the gas constant R in energy units, joules per mole Kelvin, and then also divided by the temperature in Kelvin, and then there's a negative sign there. Now notice here's one form of this equation. We've seen something kind of like this before. We've been dealing with E to a power in previous kinetics calculations. And if we take that equation and take the natural log of both sides and do a little bit of rearranging, and this is something we've seen before, we get the following equation. ln of k equals negative E sub A over R times 1 over T plus ln of A. And notice what this tells us. This is a linear relationship with 1 over T being our x and ln of k being our y. And what this means, of course, is if we were to make a graph of ln of k versus 1 over T, and be careful, ln of k will be our y value, 1 over T will be our x value. What we'd expect to get is a straight line with a slope of negative E sub A over R. And typically we do experiments where we can measure the temperature so we can determine 1 over T. We try to find the rate constant so we can get the value of K and then ln of K. And then from data at several temperatures for rate constant values, we can use that then to determine a value of the activation energy, which is kind of cool to be able to do that. Note that this is some graphical stuff again, so you'll need to know how to use your calculator to do this kind of graphing as well. You'll graph ln of K versus 1 over T. Hopefully you get a straight line. You don't have to go through several different permutations of types of things to graph. And then the slope of that straight line will equal negative E sub A over R. So let's go back to our example that we've seen previously. Temperature and rate constant value for the iodine clock reaction that we did in lab. And the question is to determine the activation energy for this reaction. Well, as we've just seen, we're going to want to take our T values in degrees Celsius, convert them to Kelvin, and then take 1 over T, and here's what we get. We're going to take our K values and take the natural log of those, and here's what we get. And then what we do is we graph ln of K versus 1 over T. We get a straight line. The equation for the straight line is y equals negative 4725 times x plus 10.44 with a fairly high correlation, but note it's negative because it's a negatively sloping line. So this means that it's a pretty straight line, but it has a negative slope. And then that slope is negative E sub A. So negative E sub A over R equals negative 4,725, which means that E sub A is negative R times the slope. R, of course, is 8.314 joules per mole Kelvin. Slope we just determined. Multiply those together. Note that we have a negative times a negative, which gives us a positive. 39,300 joules per mole, and to appropriate number of significant figures, and round it off and turn to kilojoules per mole, it's about 39 kilojoules per mole. And so what we would say is the activation energy for this iodine clock reaction is about 39 kilojoules per mole. Notice there's just one activation energy value for the reaction. Even though we use different temperatures to determine it, we don't have different activation energies at different temperatures. It's just a value. And note that it's a positive value. Always activation energies are always going to be non-negative numbers. And that's it for this screencast dealing with the effective temperature and activation energy.